Liquid solution is when the solvent is a liquid. A solid solution means solvent is a solid. Okay, it's a solid. A mixture is one where we have more than one phase. For example, in this case we have two phases. So one is water, one is solid. A solvent is the one that tries to dissolve another component. A solute is the one that we are trying to dissolve. So in this system, the solvent is the water, the solute is the salt. You look at what happens when we keep on adding salt here until we reach a point where the salt no longer dissolves. That point where the salt no longer dissolves is called the solubility limit. Here basically is the maximum solid concentration that can be dissolved in the solute. Beyond the solubility limit, this solution is called saturated. Okay? And if you add more of the solids to this, the solids no longer dissolve. So a solid solution is a solution except that it's in a solid state. So when we talk about metals, we find there are a lot of them, alloys are solid solutions. Basically, the solid solution, like a liquid solution, it is a single phase. But what you have is you have the base material. Okay, let's say your steel, the base material is your iron, but you have some other metals in this. But this actually is considered a single phase. A has the same chemical properties. So you have different types of how the solvent dissolved into a solid solution. Through this. So what is an alloy? An alloy is a mixture of metal with other metals. Okay, your alloy can be a single phase solid solution. So your base metal may absorb all your dissolve all your solutes, or it may also be a mixture of solid solutions and different phases. Okay, so for example, with this is a copper and zinc. The surrounding is a solid solution, so the zinc is actually completely dissolved in the copper. In the middle here, you have a zone, a phase with different chemical properties. So in this case, the copper and the zinc they combine to become another material with different properties. So in this case, we have one phase there, another phase there. So this is a solid solution. This is a compound of copper and zinc. Okay, so this is just a very brief introduction. Any questions? Okay, now we can look at this. So the first one here is solid solution. So I hope now you know what that solid solution is. So these are four very general ways that we can strengthen a solid. So one is by solid solution strengthening. What we do is we add a different solute in the, basically what we add is a different metal with the base metal. So when you talk about alloys, a lot of them have solid solution strengthening because we add different metals to the base metal. Another terminology is precipitate hardening. We saw just now in the copper zinc, in the middle we have a different compound. So basically, precipitates refer to those compounds which are bigger than your atoms. You may also reduce the grain size. So if you, because the grain size, the boundaries, you know what these locations are? Do you know what these locations are? What are these locations?
This location,
okay, why is it important? Okay, again, I didn't put this. I would assume that. Okay, a metal, they can deform because these locations can move. So basically, as we said, these locations are the defects in the metal. When you try to deform it, when you try to bend something, these locations are moving. So as long as you can stop the movement of these locations, you can strengthen the material. So grain size is a method. Basically, grain size is like a boundary of your classroom here. So you imagine you have more boundaries, more classrooms, it's more difficult for you to go from one side to the other side. Okay, so the grain boundaries are barriers to your dislocation movement, so therefore they can, if you reduce the grain size, you increase the number of boundaries, so you can also strengthen your solids. The last one is like your pole working. What is pole working? Add in dislocations. Why would you? Why would pole working increase the strength? So what's the difference between pole and hot? What's the difference?
Hot, the grains will fall.
It's a solid. We're talking about, when we talk about hot working, it's still below the melting temperature. I really assume that you know, right? So you know when you have a pin, right? How do we break it? When we have a pin, can you pull it, break it? Pin. So your paper clip, sorry, your paper clip. Or not a pin, your paper clip. How can you break a paper clip? Many? That's right. How many times? How many times? This is your stress strain curve. Material will have something like this. Right, this is your yield stress, we call it. This is your yield stress, this is your UTS. Sometimes there's a fracture stress. So what happens when we pole work material? Let's say we have a sheet of material. Now when you play your dough, you make your bread. Start with a lump of material. After you mix it, then you want to sheet it into a pizza base. What do? You roll it. Right? You start with a lump, you decrease the thickness. So what are you doing here? If you look at your stress strain curve, you start from zero stress, you reduce the thickness, so basically you apply a stress or strain up to that point. After it passes through a roller, what happens to it? You will want to spring back, right? Because of the elasticity. So you will follow this curve. Yes? Now imagine next, we have another set of rollers. You know you cannot just sheet it once. So you need another set of rollers. What happens here? You reduce the thickness again. So basically what you're doing is, you go back to your stress strain curve, what do? You add more stress, but the curve starts from where? A or B? So the curve starts from B. Now you can see, okay, let's say you apply a stress at that point, okay? Your load goes back. You can see here, your yield stress now is higher than your original yield stress. Right, so what happens here is that when we pole work the material, we are basically increasing the yield stress. So we are basically strengthening the material. Anyway, this is a very simplistic picture of what is happening, but I hope you get the gist. So every time we pole work a material, we turn a material from a bigger size to a smaller, or bigger dimensions to a smaller dimensions, then what we are doing is effectively, as you say, increasing the dislocations. Thereby we are increasing the yield stress. Because of that, we are strengthening. So these are four general ways of strengthening. For steels, there's an additional one. We'll talk about this. So why this solid solution strengthening mechanism? So this is your base metal, this is your lattice. You add something to it. Okay, so if you have friends, a group of friends here, I add another person from somewhere else, then you start to feel a bit strange. Okay, You start to feel a bit strange, you also start to feel a bit stressed. Right? So it's the same here. We add a foreign component here, you start to feel a bit stressed, and therefore that can strengthen the material. Okay, let's look at steel. That's just a very brief background of materials. I'm giving you a crash course in materials. So what is steel? Steel is basically iron. It's an iron material, but pure iron is very weak. So we don't use it a lot. What we find is that if we add some carbon to the iron system, our material becomes stronger. So this is where we have the steel. So steel is basically an iron system with carbon in it. We can categorize steel to different categories. So the general one would be a carbon steel. Carbon steel, basically, your main hardening agent is basically your carbon or any other metals that we add to the system are found in small quantities. We may also have what is called alloy steel, where we have significantly higher amount of other metals added to your base system. More than 2% carbon, we call this a cast iron because it's very brittle. We need to cast it. That's why it's called a cast iron. Okay, this one. I didn't include this in your slides because I presume you know this. So what is this? This is a phase diagram. Okay, if you haven't come across this, this will be quite important. If you come across it, I hope you've come across this before. So this is your quick revision. So what is a phase diagram? Phase diagram, well, y-axis is your temperature, your x-axis is your composition. So basically we start from 100% iron, 0% carbon. This is a phase diagram for the iron carbon system, okay, which is our steel system. Left hand side, 100% iron, pure iron. Then we keep on increasing our carbon. Okay, a phase diagram shows different phases at different temperatures and different compositions. Our important region will be around here because this is for the steel. We see that at room temperature, okay, room temperature, which is actually below this. The stable phases for our steel are two phases. One is called ferrite, which is our alpha iron. The other one is called a cementite, which is a compound between iron and carbon. So we talk about a stable phase for steel at room temperature. We should find two phases. But what's interesting is when we increase the temperature, we start to see we start to see changes in your phases. So the important thing here will be this region, which is your austenite region. So basically, if you increase the temperature, at a certain temperature, you start to get austenite. Basically, you are transforming your two phases, which are stable at your room temperature, into a different phase. Okay. So at this temperature, this is called the eutectoid temperature. This is where the transformation of your two phases to your austenite or vice versa start to happen. So let's say we heat up to this region, to the austenite region, and then we cool down. So at that temperature, 727, what happens? Your austenite is transformed to two phases. One is your cementite, and the other is your ferrite. So at room temperature, if you do a metallurgical analysis, you find your steel to be consisting of something like this, okay, which is basically a lamella layers. One layer is your cementite, the other layer is your ferrite. And this is called pearlite because the appearance looks like a pearl. Okay, this is a stable, and we do it very, very slowly. And we cool down very, very slowly. We change the temperature very, very slowly. That is what we get. Okay? Now this shows an isothermal transformation diagram for your steel. So this is a temperature, that is a type. So effectively what we are trying to do here is we heat up already to the austenite region. higher temperature, your austenite phase is stable, and then we cool down. Here says isothermal because when we cool down, basically what we do is we cool down very quickly initially, and then we hold our steel at a constant temperature. So basically, we are going through this path horizontally. Okay, we cool down very quickly. Let's say we want to cool it to 600 degrees, cool very quickly, and then we hold our material at 600 degrees, so we are going horizontally across. Okay, when we do this, we can get different microstructures. So what happened here, we start off from there. Okay, we start off from there, we cool down very quickly. Let's say we go to 600 degrees C, we hold it over some time. These lines represent the transformation of our austenite to different microstructures and microstructures, final microstructures. We cool down 600, we hold it. You can see that our austenite here, 100% austenite, becomes gradually is transformed into a different microstructure. In this case, if it's 600 degrees C, it's going to be a pearlite microstructure. Okay, cool down very quickly, hold it, isothermal, we get pearlite. We cool down to a lower temperature, let's say 400 degrees C, we hold it, we hold the temperature, we go across here, we end up with a binite microstructure. If we pull it very, very quickly all the way down to lower temperature, we get what is called the martensite. And the martensite is the one that gives our steel very interesting properties. Okay? So basically what happens here is that we pull it very, very quickly, we pull our material very, very quickly from austenite to a very low temperature, we start to form martensite. So martensite gives us a very hardened steel, okay? But there are three conditions for martensite to occur. One is our steels must have enough carbon. So typically it's about 0.3% carbon content. Anything lower than this, anything lower than your 0.3%, so basically your low carbon steels, you cannot form martensite. But at least if you form martensite, it's very little. So you don't get a lot of hardening. Okay, so you're talking about steels with high enough carbon, got that? And you must hit this to the austenite region. You must hit your steel all the way to that region so that you can form martensite. And this is followed by a quench. After we heat up, we need to quench it. Why do we say quench it? Quench it means we pull it very, very quickly. Okay, we pull it very, very quickly. So what happens here is we need to heat up the steel. The steel must have more than must have sufficient amount of carbon, basically more than about 0.25%, 0.3% of your carbon. After we heat up to the austenite region, we quench it. We dip it in water, we can dip it in oil. Okay, basically this is what we're doing. We dip it in a cold liquid. When we do this, we get what is called the martensite. The martensite is very interesting because if you look at this, this is a hardness. This is versus the amount of carbon. Okay. If you look at martensite, if you compare to your pearlite, the hardness and the strength are much higher than your pearlite. Okay, this is why we're interested in the martensite. This is why previously during the lecture we talk about reduction hardening and fixed hardening, because what we say is we want to convert our steel, transform our steel into martensite, because martensite gives us high strength, high hardness. Martensite, something that's very hard, something that's very strong, is also tends to be very brittle. So we need to be very careful when we deal with martensite. So what we also do is what is called a temper. Okay, I'm not sure if you come across it. When you look at your materials, you see a word temper. Tempering, what does tempering mean? Basically, if you look at this diagram, this is the temperature versus time. We started from there, high temperature, we quench it. To a low temperature, we form martensite. Okay? What tempering means is that when we increase the temperature up to a certain temperature, we hold it there. When we hold it, the martensite microstructure starts to transform itself into the more stable phases, which are your cementite and your ferrite. When we do this, you look at this, is a hardness versus composition. Basically, the properties of your martensite is reduced because it's now become tempered. Okay, but it's still better than your perlite. So this is a very typical heat treatment for our steel. We quench it before martensite because martensite is too brittle. We then temper it so that we get a moderately strong material with a higher ductility, which is better than our stable phase. Do you know how we can get this stable phase? Do you know the term that we use? What's the heat treatment term that we use to get this stable phase? We get perlite. Sorry? I thought you have it. No? Okay, we'll come across that here or later. Okay, so we look at this. Okay, these are different heat treatments of steel. If you look at any steel literature, you may find these terms. Okay, first is what we've done just now. It's basically bulk hardening. The whole sample or whole material, you quench it. Okay, you heat up, then you quench it, you get your martensite. You have also what is called the paste hardening. Paste hardening is probably what you see in your shafts and your gears. What this is it's basically paste means just the surface. You only harden the surface, you don't harden the inside. Because we still want some ductility in our components, we only want a hard surface. A hard surface is good because fatigue normally starts from the surface. A harder surface means a higher resistance to fatigue. Okay, so typically we want a hard surface. It's the same thing as your bulk hardening, except that right now what we do is we just heat up the surface. Okay, so we have what is called direct hardening. In this case, we austenize and we quench. This one is only for the surface. There are two ways of doing this. One is flame, one is induction. And this is for steels which have sufficient amount of carbon. For steels which have not enough carbon in it, we have to do something. For example, we have to introduce carbon to our steel. So that's why we have this kind of diffusion. These are for hardening. You can also see for softening, recrystallization. For example, hot working. What happens during hot working? As you said, the grains they change. Actually, what formal term is that they recrystallize. Okay. You also have annealing. How do we achieve perlite? Basically, it's through annealing. Okay. Anyway, let's look at your paste hardening because this is what you see. You look at your gears. Okay. So the surface be hardened. If you look at your shaft surface will also be hardened. So basically what we're doing here is like your brake, okay? The brake has a hard surface, but inside is soft. And this is what we see here. So this is what is called direct hardening. Basically what we do is we heat up the surface and then we quench it. And this is we quench it so that we can form martensite on the surface. And this is used for steels with sufficient amount of carbon. As we said, we need at least about 0.25 to 0.3% of carbon to get our martensite. So this is one method in case harden. So this is a flame hardening. Essentially what it is that we just apply a flame, okay, on our surface, and then we quench it with water. So this is one example. Basically, in this video, what they're trying to do is to heat up a sample using flame. You have to heat up to the austenite region. You can see there's a pool of liquid. I think there's water. So what you do is you quench it. Okay, so basically you quench it. When you quench it, you get martensite. Okay. This induction hardening, we saw this induction hardening in one of the lectures earlier. what it is basically you do the same thing as the flame, but instead of using the flame, you're actually using electrical resistance to increase the temperature of your material. And once you increase your surface, the temperature of your surface, you just keep it, just quench it in water. Diffusion hardening are used when the steels do not have enough carbon content. So just now the two methods we saw, we quench it, we heat and we quench. Those are for steels with enough carbon content. For steels with insufficient carbon content, we need to add other elements to our steel. So let's say we have a low carbon steel. Okay, low carbon steel, we cannot quench it or cannot heat it and quench it to form andesite. What we do is to expose it to a high carbon environment so that carbon can penetrate into our steel, and then subsequently we can do quench and heat and quench to get andesite. So this is what effectively what's happening. So this is for carburizing. Carburizing, what we do is we put a sample in a chamber, we add a hot gas which contains carbon, and the carbon can penetrate to the surface, and then we bring this sample, because it's hot already, we quench it to get our andesite on the surface. Okay, there are different. This is about carbon. You can also add nitrogen to this and other elements to get your carbon. We talk about annealing. What is annealing? Look at this curve again. Although this is basically not exactly correct for annealing, but it's okay. I think this gives you the picture. Okay, this is your TTT diagram again. We heat up to the austenite region. When we talk about full annealing, what we do is we switch off the oven. Okay, we put our material in the oven, we heat it up, get our austenite, then we switch off the oven. And we leave our samples, we leave our materials in the oven to slowly cool down. Basically what we are doing here is to slowly cool down. When we slowly cool down, we get our perlite microstructure. Normalizing is similar to annealing, except that we, instead of leaving our materials in the oven, we pick them up from the oven, we put it on the air outside because the cooling rate is faster. Okay. Crash course in steels. Okay, next one we just look at very briefly different categories of steel, so that when you go to your CES, you won't be so lost. So we look at carbon steel. We look at HSLA. This is HSLA, high strength low alloy steel. We look at ultra high strength steel. Very quickly go through stainless steels, different types of stainless steels. Very quickly, okay? There are also different types of steel. Two steels are the steels that you use for tooling. So we talk about these rollers. You use two steels for the rollers. We also have cast iron, but we normally do not use cast iron so much except particular applications. So you talk about carbon steel, first thing you notice is all these numbers. Okay, so you specify to your supplier, I want these numbers. These numbers, basically the first two numbers signify the primary alloys. So for example, when you do not have any other major alloy added to your steel, the number is 1. Start with number 1. So you talk about mild steel, it's basically 10 something. You talk about medium carbon steel, you still talk about 10 something. Talk about high carbon steel, it's also 10 something. Then the rest are basically you have different types of elements added to your steel. The two that are of particular importance to you will be this, the molybdenum steels and your chromium molybdenum steels, because these are used a lot for machine parts. Okay, so basically the first two numbers signify the primary alloys, the last two numbers signify the amount of carbon. So if you look at this, if I tell you it's a 1030 steel, it's a 1030 steel. This one is a carbon steel with about 0.3%, 0.3 carbon. Okay, so likelihood, I think if you go to your supplier here, I think likelihood they will supply you with this, which is 0.45% of steel. If you want a medium carbon steel, I believe this is what they normally stock. 1045. I think they also stock a 1080 if I'm not mistaken. I think that is too high already. Okay, so this one is important. This one also you may see a 4040. So this is a polyethylene steel with 0.3%. Okay, so when you go to your manufacturer, you don't just tell them I want a steel. If you want a carbon steel, you better tell them what grade you want. And most likely, and I think we'll go through afterwards, it's going to be something between these two. I'm not sure if they stock this, but it's going to be a 4 or something. But for your case, most likely you'll be using this because this is sufficient for your applications. HSLA, what are HSLA steels? This one, they have special chemical composition so that they can achieve higher mechanical properties from your carbon steel. They have higher properties without relying on your martensite hardening. Okay, they have basically low carbon, so you do not form martensites, but you add a lot of alloys. Add a lot of alloys so that you can get your higher properties. And HSLA steels are used mainly for large structural applications. For example, you look at a bridge, it's very large. When it's very large, you can understand that it's very difficult to put in an oven because you need a very big oven to heat up to form your martensite. So therefore, you do not try to heat this up. Not only that, for these structural applications, you need to weld them. Okay, when you weld them, if you form martensite, then you are in big trouble because the martensites are very brittle. So what you want when you want to weld the material, you try to avoid a material that form martensite. So a low carbon is important here because we will not give you martensite, so our HSLAs will be welded. Ultra high strength steels, I think there was an error in the slides. This should be about 1,400 MPa. So your HSLA are actually quite good, quite strong materials already. Your ultra high strength steels are even higher. Okay, these are your chrome polys. Talk about this material. Like I said, this may be a bit good for your application. You can also talk about some nickel steels as well. And the steels for car bodies also tend to have very high strength. I think only have one slide on stainless steel, right? Okay. Stainless steel, this picture basically shows an overview. Okay, the basic steel, stainless steel is that is your ferritic stainless steel. Basically, okay, by the way, why is stainless steel stainless? Why is stainless steel stainless? What's the difference between stainless steel and carbon steel? Sorry. Okay, what is meant by stainless? Less prone to rusting. Okay, so it is more corrosion resistant. Why is it more corrosion resistant? What are the elements? The main one is what? Actually, you know about all this already. So, the main element is what? The main element is chromium. Okay, you have about 16 to 20% of chromium in this. So our ferritic stainless steel has a ferrite microstructure. It's basically steel plus a lot of chromium, basically about 16 to 20% of chromium. That's why we can get the stainless steel. This is a basic. When you add nickel, okay, this phase they want to transform. When you add nickel, they want to transform to what is called austenite phase. So when you add a bit of nickel, you can get somewhat a composite. Basically, it contains a ferrite phase and an austenite phase. If you add more nickel, then you transform the whole ferritic stainless steel to what is called austenitic stainless steel. Basically, this is a different microstructure. Okay, it's austenite microstructure, and therefore we call it austenitic stainless steel. So in between this, we call this duplex stainless steel. Okay, duplex stainless steel. Basically, duplex stainless steel, we have it because it has the advantages of both the austenitic and the ferritic stainless steels. If you look at your ferritic stainless steel, it has very low carbon content. So if you add carbon to this ferritic stainless steel, we have what is called martensitic stainless steel. Why do we call it martensitic stainless steel? Because we have enough carbon content to be able to form martensites in our stainless steel. So this one is something that we will want when we want a very hard material. Hard stainless steel, we will go for martensitic stainless steel. So the majority of the stainless steels are this one, austenitic stainless steel. Okay, you're very familiar with this 304, 316. Sometimes you also see this symbol, these numbers. In 0, in 10. Actually, basically, these do not mean anything as far as the formal definition is concerned, but basically they tell you that this is just chromium plus nickel, which is basically your 304. This one has some molybdenum in it, which is 316. So 304 is your basic austenitic stainless steel. 316 has some molybdenum added. These two are your most common stainless steel around. So I think let's go through a very quick Q&A. Your cutleries, what type of steel is used here? What kind of stainless steel? Martensite? Martensitic stainless steel? So first, it has to be stainless because we're using with food. So you're left with only a few options. Okay, this is most of it will be 304, 316. The cheaper ones, those are very cheap ones, will be 304, 316. But it should be generally it should be 304, 316. You have an induction cooker. Your pot is made of what? Stainless steel. What type of stainless steel? What type of stainless steel? Why high carbon? Okay, you're almost there. What we need here is the stainless steel has to be magnetic. Okay, for the induction cooker to work. Austenitic stainless steel is not magnetic. Ferritic stainless steel is magnetic. So this one should be a ferritic stainless steel. Now, Art Science Museum, it has quite a lot of reflective patterns. What kind of steel is used here? Is it used as a structure, weights? So you will go for stainless steel, normal battery. So this we use 316 stainless steel for the reflective panels. Your knife.
Two steel.
From steel? Two steel. Possibly. But
Yeah,
this is for general home use.
Home use.
脆弱什么的。
Magnetic stainless steel. So you talk about a very sharp edge, you need a very hard material. So you're going to use martensite. One needs to be corrosive, resistance. So you're going to use a stainless steel. Okay, next page.
我觉得参考中的时候，我觉得是，因为你需要一个 strength 这个走过。对啊，我找一天我去那边。
Keep close to the sea.
不能有，太帅。我很少去这边。我每次要去的时候，都是有那种 event 的时候。那每次我们只要驾车过来，我们就只回家。
Oil platform. Components in the oil platform.
就所以就去不跟他们。
Use stainless steel.
你男朋友应该可以带你
Talk about seawater.
游戏吗？
Most likely you'll be using a reflex.
回来跟黄森带，回来跟。
是吗？
By the way, stress corrosion cracking is something that you find.
stainless steel，他们是用 normal steel，靠边 stainless steel 那个。
That might be is based on the problem of stress corrosion. Your northeast line, 3 years ago, there was a breakdown. There were 2 breakdowns. The 2 breakdowns were due to stress corrosion cracking of your austenitic stainless steel. So you use austenitic stainless steel for one boat and the wire. In both incidents, the boat failed and the wire failed due to stress corrosion cracking. Do you know what stress corrosion cracking is? You can Google. Or you want to know? Okay.
它里面口容量但是太过大，就有 cracks。
It's something that is peculiar to
买的特别少，现
turns out that your austenitic stainless steel is more susceptible to stress corrosion cracking. Okay, this is due to something which is called sensitization. So if this is your grain, this is your grain in your stainless steel, austenitic stainless steel, you have your carbon. Okay, you have your carbon. What happens when you heat up to a relatively temperature which is about 400 to 600 degrees C? Your carbon starts to have a lot of energy. Okay, what it does is it likes to go to the grain boundaries. It starts to migrate to the grain boundaries. So you have chromium all over the steel. What happens to the chromium and the grain boundaries? They start to combine with your carbon to form a compound. This is high temperature, okay? Basically when you weld an austenitic stainless steel, when you do hot working, your austenitic stainless steel, this will happen. Your chromium combines with your carbon, form a compound. What happens? The chromium no longer is effective because it's tied up in a compound. You no longer have chromium at the grain boundaries. And what this means is that corrosion will happen at your grain boundaries. And why do we have stress? Stress corrosion cracking. What happens is normally your stainless steel you want to apply load to it, right? So let's say you have a stress, apply a stress to your steel. This corrosion at the grain boundaries will cause a crack. What turns out to be the cracks, the grain boundaries become cracked. So these grain boundaries become detached from each other. This is your crack. This is because your corrosion is happening at the grain boundaries. Basically, this is a very snapshot of what is meant by stress corrosion cracking, and it only happens, it tends to happen in your austenitic stainless steel. That's why you have the Week5 stainless steel, because your ferritic stainless steel will arrest your stress corrosion cracking. But your ferritic stainless steel also has its own problem, so that's why you mix them, get the benefit of both ferritic. This is a Doha International Airport. Oh, sorry, I gave you the answer already. Okay.
可以了，这边 duplex。
我也没有看到，我看到了，
自己看到了。
弄一圈线。
Back to earth. Back to a very humble application. Your I-beams in your structures. What will you use? And through this now very quickly. Large structural tools, structural applications. HSLA. Okay, high strength flow alloy steel, because we want to weld this, because these are too big to put in our oven. We cannot put this in our oven to harden it. So we need to use high strength, which is based on chemical composition. First nest, China, Beijing. First nest stadium. Same as a structural application, high strength low alloy steel. Machine. Anyone who's able to get it?
有可能呢，因为口就很高。
Marine steel.
然后他们就放超过prevent the corrosion.
Okay, this is another big structural application. So again, like this is high strength alloy.
对对对对对。这个不是这样。
Back to your campus, see a lot of stainless steels in your lift, for example, in your buildings. What steel is
有
this?
可能呢，因为这个是另外一个，每个部位不同。还有，而且我们讲那个楼梯的这个什么，
Like we put ferritic stainless steel, because this one you can stretch it to become thin. Look up one actually. Piping. What will you use for piping? Talk about underground piping or big piping.
一边的，他说他们在看外面给他们做工。
Master 的 PVC。
Don't need to be certified.
应该不需要。
What is it? Will it not be stainless steel? So, the reason, okay, I took up because I thought it's not so relevant. But last week I had checked with Semcop boss, to talk about this piping. You use stainless steels, duplex steels, but apparently they've changed their piping to high density polyester.
2个还3个老板都是这个板，
Good question.
是老板。
Uh,
都很多耶。
question. How to change the underground piping to
然后这是看去，看去 station 的时候有3个老板，
generally your polymers
真的
are
的
less
板。
okay, but in terms of the stresses, low pairing, they are less strong. But I would guess they change it because it's less corrosive, so that they need less machines.
So it's cheaper.
It's not necessarily cheaper, okay? To use polymers is not necessarily cheaper. In fact, he told me it's not. But the maintenance is actually because with this you have corrosion, and your corrosion you have to monitor. Let's say you say but the pipe, the HDB or the polymers, they tend to have HDB less corrosive. So you talk about acids, for example, use glass contain acids. Because glass is less. The problem with the polymers is actually how you stick them together. Okay, with metals you can grab them. Apparently Semcon is also using grab
另外那个
polymer parts. ，Okay, this is of concern to you. Your car axle, what material will you use?
係啊。我看到这个是 ultra strength.
Okay, one of this. Okay, for your application, I think this one will be sufficient because your shafts, this one should be sufficient. But you do some calculation. Okay, but I think this one should be sufficient. So if you want a stronger steel, you should be using or the common material will be your chrome oil steel. This is your 41 and 43 on this series. Car body is actually quite interesting because there are a lot of different types of steels that are being used. So you come across, if you look at literature on car bodies, there are different types of steels. Okay. Sometimes you put in. So one of these is your dual face steel, which is consists of the ferrite and andesite faces. So you can see these are used for your car bodies. Again, like I said, if you Google, you can find different types of steels which are being developed for the car bodies. This is a landing gear for your space shuttle. Basically, we are talking about very high strength here. So, not surprised we use ultra high strength steel for this kind of applications. More humble application, steel cans, you see them.
这种偏有用 steel 的。
Nowadays, so you still see them around them. What are they?
在这两边。
What type of steel?
国那里。
Arm steel, low carbon steel.
看电视上，我下你也认识。
Okay, I think I'm overrunning here. Okay, just one part on aluminium. Aluminium, we will talk about andesite. We talk about precipitates. Precipitates are basically just within your matrix, base metal, you have a compound. Basically, this is bigger than this is not just an atom. It's basically made up of different atoms coming together to form a compound. So you look under a microscope, you can see this as basically blocks. Okay, and these precipitates, they are pink so that they hinder the movement of the dislocations and therefore strengthening. To understand precipitates, you need to understand your phase diagram. Okay?
Hey guys! Do you want to learn how to make pretty candy that you can give to your friends and family? Then in this video I will show you how to make rock candy. It's easy and fun to make, you just need to be a little bit patient and have fun experimenting. For this project you are going to need 1 cup of water, about 3.5 cups of sugar, food coloring, jars. You will also need lollipop sticks or skewers and clothespins. Add the cup of water into a big saucepan. Then start adding the sugar cup by cup. Stir while adding the sugar and let each cup dissolve before adding another cup of sugar. The more sugar you add, the longer it will take to dissolve, so be patient. Then take your skewers or lollipop sticks and dip them into the solution. Make sure to cover only the area of the stick where you want the candy to grow later. Then place the sticks over a plate and start coating the stick with some sugar. This way we give the new sugar crystals something to see to. Be sure to let them dry all the way, or otherwise the sugar coating will fall off when you put them into the hot sugar solution. In the meantime, continue adding sugar until 3.5 cups of sugar have absorbed. Then let the sugar water boil for about 10 minutes so you can be sure that everything is absorbed. If you want, you can also add some flavor into the liquid so it's kind of like a delicious lollipop in the end. If you still see some sugar crystals, add a little bit of water very carefully so they can't dissolve in it. Now you can either add food coloring directly to the saucepan or add it to the jar later. Then turn off the heat and take the pot off the hot plate and let it cool down for about 10 minutes. Then pour the solution into one of your jars. Before I added the skewers, I let the jars cool down a little bit longer until the glass didn't feel so hot. After that, slowly insert your sugared skewers into the solution. I use 2 clothespins to keep the sticks in place. Make sure that your sticks are not touching the sides, bottom of the glass, or each other since they need room for the new crystals to grow. Once you have your skewers or lollipop sticks hanging in the jar, you shouldn't move it at all. Let it sit quietly undisturbed for about 3 to 7 days to see the results. Don't touch the skewers, but pay attention to it as well. And if everything went well, your rock candy should look something like this. I experimented with different kinds of methods, and I tried to find the right sugar and water ratio. And I have...
Okay, what's happening here? Why does it crystallize?
Because of the sugar. Too much sugar 而且做完
So what does the person do? He has a solution, sugar solution. He heated up the water, dissolved the sugar, and then let it to cool down. Then she stick something to it, and then does it happen with any other sugar solutions? Does it have to be a particular type of sugar solution? I know I've taken a lot of your time, but if you want to go for your so what type of sugar solution? Is there a science behind this? Must you say yes? Okay, for those of you who came earlier, you talked about the phase diagram. So this is a phase diagram for your sugar water. Okay, this is 100% water, 0% sugar. As you add sugar, this one is 100% sugar, this is 0% water. So these are different phases. This is a liquid solution. What's the liquid solution? It is a solution where the solvent is a liquid. Solid solution means the solvent is a solid, right? It's a liquid solution. This part is your liquid solution plus your solid sugar. You remember initially I gave the example with salt. Add salt to your water. Up to a certain point, salt no longer dissolves. You get solid salt. So in this case, it's sugar. You get solid sugar. And this is your solubility limit. This is solubility limit. Solubility limit is your maximum concentration of your solute in your solvent. So what this graph shows is that as you increase the temperature, you can dissolve more sugar in your water. Right? If you look at this, you can dissolve about 62% in water, 0 degrees C. At 18 degrees C, you can dissolve about 74% of sugar in your water. So just now the candy, what are we trying to do? To make the candy, we are trying to do this. Okay, we heat up our sugar solution up to that point. Right, up to that point, we do not have any extra sugar, so it's still within this liquid solution. And then we cool down. Basically, we cool down the solution past this point. This is our solubility limit. Past this point, somehow we still have a liquid solution. Okay, and that liquid solution is called supersaturated. So it means by supersaturated means the sugar is supposed to come out, but it doesn't come out. It remains in the liquid, but it's not stable. It's supersaturated. So when we dip the candy stick with sugar particles, basically the particles are trying to seed, called seed, okay? Try to seed, it's a seed so that all this sugar that is extra, they can latch onto your sugar particles, solid particles, so that they start to grow on your candy. So all this extra sugar that is not supposed to be